Okay, guys, good morning. So, today we'll be starting with the numerical section of the chapter, right, which is mechanical properties of fluids. We have talked about the next chapter in our live class, I hope so. So, today we'll be completing the numerical section of the chapter. Okay, so I hope you remember almost all the equations which we have taught or which I have taught and you have learned from this chapter. This is a very good chapter regarding numerical section. Okay. So first part questions, I will just reading it out. I recommend you guys to listen to the question while I'm reading and write it down as it is. Okay, later on of the questions, I will take the photo. I have taken the photographs and I will show you. So the first question is, water stands at a water stands at a depth h in a vertical tank. A hole is made on the wall of the tank at a depth h below the water surface. Find the distance from the foot of the tank where the water stream will strike the ground. So I'll draw the question. I'm not going to read the question again, guys. You guys can pause the video and then listen to the question. So this is a water tank, right? There is an orifice here, right? And the water level inside this tank is given as capital H. And this orifice or the hole is at a small h distance from the surface, and the water will be dropping like this, right? So there will be a particular range till where the water can reach. You are asked what is the value of this one. Clear? Right? So this is a question. You are asked an expression for it. So u is the initial velocity with which the water comes. You know that it will be 2gh, right? Orsel's law, right? And you also see, when you see this height minus this h, that is at this much height, right? So you this projectile motion, so what will be this height? It will be h minus small h, and from there an object is falling. Means obviously it is water, but we are going to assume that is an object, right? So this height you can write h minus h is equal to half gt square, right? Clear? A freely falling body. Now from here, can't I write T is equal to root of 2h minus h divided by g? Yes. Now this is just like range, right? Horizontal range. Horizontal range is equal to initial velocity into the time which is required by the body to reach here into the initial velocity. You have found initial velocity already, 2gh, into time you have found it as root of 2 h minus h by g, right? You can cancel gg terms, right? Clear? And 2 root 2, that is root 2 into root 2 is 2 into h minus h. You got an expression, right? It's a simple question. I want to start it with a simple question. Now the next question, second one. 0.2 centimeter liquid column, around 0.2 centimeter liquid column balances an excess pressure inside a soap bubble of a radius 7.5 mm. Find the density of the liquid if the surface tension of the soap solution is 0.03 Newton per meter. A 0.2 centimeter liquid column is there. It balances an excess pressure inside a soap bubble of radius 7.5 mm. You are asked what is the density of the fluid if the surface tension is given as this much. Clear? Right. So you know about the soap bubble, right? What is the expression for excess pressure? P is equal to 4s, right? It is having two free surfaces. So it is 4s by r. Now that is maintained, this excess pressure is maintained by a column. So column pressure means it is h rho g. So from this term I can find rho, right? Your asked point is rho. Rho is equal to 4s by r into hg, right? Now 4, what is the surface tension? It is 0.03 divided by how much is the radius given? 7.5 mm. So 7.5 into 10 to the power minus 3 into how much is the height of the column? It is 0.2 into 10 to the power minus 2, and g is 10, or you can take 9.8. You will find rho is equal to 8.2 into 10 to the power 2 kilogram per meter cube. Calculation, I recommend you guys to do it by yourself, right? It's a simple question, just understand the logic. Now the third question, a capillary tube of 0.2 mm radius is dipped vertically in water, right, like this. Right, if the surface tension of the water is given as 0.75 Newton per meter, density of water is given as 1000 kilogram per meter cube, and G is given as 10 meter per second square. Find the height of water column. So it is again easy, right? So capillary rise is happening here, right? So you are asked how much is the capillary rise. That is what is meaning. There is your capillary tube is dipped in water and there is a surface tension, density, etc. is given. You are asked what is the height of the water column. So you are asked what is the capillary rise. So you have learned the expression for it. 2s cos theta divided by rho Ag or rho Rg. R is or A is the radius of the capillary tube, right? So 2 into surface tension is 0.075 into 1 cos theta. Why did I take it as cos theta as 1? See guys, it is water. So most of the time cos theta we take for water as 1. Keep that in mind, okay? And rho is given as 0.2 into 10 to power minus 3. Right, into 10 to power 3 into 10, right? You will get H as around 7.5 centimeter. Clear? Right, let us move on to the next question. I believe it is fourth one, right? An air bubble of radius 1 mm lies at a depth of 10 centimeter from the free surface, like this. Right, this one's radius is 1 mm, right? If the surface tension of the water or the liquid is given as 0.075 Newton per meter and density is obviously it is water 10 to the power 3 kilogram per meter cube, by what amount is the pressure inside the bubble greater than the atmospheric pressure? You ask how much is the pressure difference. Clear? Right, so we have to analyze this question a little bit. Oh, sorry, why did I bring this one? Okay, see, so you are given a scenario like this. So there will be some pressure here and there will be some atmospheric pressure. You are asked what is the pressure difference. Clear? So let us say the atmospheric pressure, I am going to take this as P naught, right? And I am going to take the pressure just outside the bubble. Let us say it is P here. So this is atmospheric pressure, this is the pressure just outside the bubble. So I can say at this level, right? So this is the level, right? So this is the pressure P over here. So this is the H, right? So P pressure at this section is equal to atmospheric pressure plus H rho G, right? Now let us talk about the pressure inside the bubble. Let's say the inside bubble is having pressure P dash. Now P dash will be having pressure more than this atmospheric, this pressure point. This, let me draw this figure a little bit large. Oh no, I can enlarge it now. Right, see, when I just consider this bubble section only, inside the bubble is having pressure P dash, right? It is having pressure P dash. Now inside pressure of the bubble and just outside the pressure, right, outside point of the bubble, P minus P dash, that is the excess pressure of the bubble, right? So excess pressure of the bubble is P dash minus P, right? P dash minus P, right? That is equal to bubble, right, inside the liquid 2S by R, right? Clear? Now you got two expressions, you have to just solve it. Right, you can just substitute P from this formula so that this becomes P dash minus P naught, right, minus H rho G is equal to 2S by R, right, or P dash minus P naught. That is the question. You are asked what is the pressure difference between the bubbles inside pressure and atmospheric pressure, right? So P dash minus P, oh, why did I write dash over here? P naught is equal to 2S by R plus H rho G, right? Now H is how much? Is given as 10 centimeters, so 0.1. Rho is given as 10 to power 3. G is 10. plus 2 into 0.075 divided by radius is 1 mm, right? 10 to the power minus 3. So you will get it around 1130 Pascal. Clear? Right? Very easy. Now similarly, I believe this fourth question is over. We'll go for the fifth question. An air bubble of diameter 2 mm rises steadily through a solution of density 1750 kilogram per meter cube at a rate of 0.35 centimeter per second. Find the coefficient of viscosity of the solution. You are asked to neglect the density of air. So there is a solution. An air bubble is trying to come up to the surface, right? And it is coming up with the velocity this much, and the density of the liquid is this much, and the diameter of this bubble is this much. You're asked what is the coefficient of viscosity, right? So I hope you remember buoyancy term, etc. Right? So the force of buoyancy, which is the upthrust, is equal to the weight of the fluid displaced, right? So buoyancy, if I rate B, is equal to, is a force, right? So it is actually V rho G. That is how you have learned. So what is V here? That is the volume of the bubble. 4 pi r cube. Let us make this a small r cube. Small r cube, right? Into density into G, right? This is the upward force, right? And there is a viscous force which is against the motion, which is downwards. And that viscous force is equal to 6 pi r eta v. Yes. Now, and since we are neglecting the weight, these two forces should be equal. That is the buoyancy upwards and the viscous force downward should be equal. So I can write it as 6 pi r eta v is equal to 4 by 3 pi r cube rho g, right? Clear? From there you can find eta is equal to 2 by 9 r squared rho g, rho or sigma g, this is sigma, into 9 into v, right? Please substitute the values. It is 2 by 9, 1 into 10 to power minus 3 whole square, 1750, 10 divided by 0.35 into 10 to power minus 2, you will get 11 Poise as answer. Poisson, but you can make it as Poise. Clear? Alright. Now next question is sixth one. Find the terminal velocity of a raindrop of radius 0.01 mm. Right? Coefficient of viscosity of air is given as 1.8 into 10 to power minus 5 newtons second per meter square. Right? And density is given as 1.2 kilogram per meter cube, right? And density of water is given as 10 to power 3 kilogram per meter cube, and you are given G as 10 meter per second square, right? So this also you have learned, guys, and you have just derived the equation, right? So from that is from 6 pi eta rv, okay, and 4 by 3 pi r cube rho g. From here you just find the velocities expression. Just calculation is pending. You will find v is equal to 1.2 centimeter per second. I am not going to write the substitution, etc. It is very easy. Now the next question, I believe sixth question, right? A water is filled in a flask up to a height of 20 centimeter. The bottom of the flask is circular with a radius 10 centimeter. If the atmospheric pressure is given as 1.01 into 10 to the power 5 Pascal, and find the force exerted on the water column if G is equal to 10 meter per second squared and density of water is given as 1000 kilogram per meter cube. So you are asked, there is a flask, right, like this, right, and to a height of 20 centimeter, right, the water is there. right? At the bottom of the flask is circular and this one's radius is 10 centimeter, right? If the atmospheric pressure is this much, let's say I will write it just like P naught, right? Find the force exerted on the water column, right? So you are having this, so let's say this much 20 centimeter, let's say I'm going to consider a point here, right? So the pressure at the bottom section P will be equal to P naught plus H rho G. I'm starting the solution, okay, right? So P naught is 1.01 into 10 to power 5 plus, what is the 20 centimeter? I will write it as 0.2, then 10 to power 3 density of water, and G is 10. You will find it as 1.03 into 10 to power 5 Pascal is the pressure at this point, that is the lowest point. Now area at the bottom side is pi r squared, right? So I can find it as 0.0314 meters square, right? Substitute the radius there. So what is the force at the bottom? It will be pressure into area, right? So 1.03 into 10 to power 5 into 0.0314, right? So you will find the answer as 3230 Newton. Clear? Simple question, simple answer, right? Clear? Similarly, let us move on to the next question, that is 7th one. A 700 gram of solid cube of length 10 centimeter, right, floats in water. If the density of water is given as 10 to power 3 kilogram per meter cube, find the volume of the cube outside the water. So this is a scenario. You are having a tub that's like this, right? It is filled with water, and a cube, let's draw it like this. I am only drawing a side view, okay? A part of it is outward and outside, some of them is inside. And the solid cube is having cube, na? So this is 10, right? So all the sides will be, and this one's mass is 700 gram, right? And density is given. You are asked how much is the volume of cube is outside the water. You're asked how much is this much shaded portion's volume. Clear? Now this question type I have done in your live class, right? So weight of the cube, this weight of the cube, right, should be balanced by the buoyancy, and the force of the buoyancy is how much? It is equal to the weight of the water displaced. I talked about it, right? So how much weight is displaced by this object is what is causing the buoyancy, right? So let us say V, capital V, is the volume of the cube which is inside. This much portion's volume is V, right? So the weight, so that much V will of volume of water is displaced now, right? So what will be the weight of water displaced? Weight is equal to V rho G, right? I will write weight of water displaced is equal to volume of water displaced into density of water into G. Now how much is the volume of water displaced? This much portion is displaced, right? So in place of volume of water, I can write this as volume of the cube inside the water, right? So that is V, right? So V into how much is the density of water? Density of water is 1000, I believe we have given 1000, and G is 10, right? Clear? I believe how much is given? 10,000, okay. Clear? This much is clear, right? Now this much volume or this much water which has been displaced is actually balanced by this mass of cube, right? Right, how much water or how much buoyancy it is receiving from this end is balancing the weight of the cube. And what is the weight of the cube? It is mg. The weight of cube is equal to mg, that is 0.7 into g. So these two things are balancing. So from here I can get volume. You just have to substitute, equate it. You will get V is equal to 700 centimeter cube, right? Now that means inside portion is how much? 700 centimeter cube. You are given the total volume. How can I find the total volume? 10 into 10 into 10, that is 1000 centimeter cube is the total volume, is 1000 centimeter cube. So 700 centimeter cube of volume is downwards, means 300 centimeter cube volume is above. right? So that is the answer. Clear? Right? Now, similarly, let us move on to the next question. I believe it is 8th question or 7th. Which one? 8th question. The question is, a piece of pure gold, the gold is having a density 9.3 gram per centimeter cube, is suspected to be hollow inside, right? That is like this, and this center portion is nothing, right? Now, it weighs 38.250 gram in air, and it weighs 33.865 grams in water. So it is losing some weight in water, right? You're asked what is the volume of the hollow portion of the cube. I believe we have done this type of question, right? You're asked what is the hollow portion's volume. Clear? This question, guys. See, first let us find what is the volume of this gold piece, because its mass and density is given, right? So mass by density, so it is 38.250 divided by 4.113, right? This is it's 9.3, no, sorry, this is 9.3. So you will get the answer as 4.113 centimeter cube, right? So this is the volume of the gold piece. Now once it is dipped in water, it is losing some weight. How much loss is happening? Its initial weight is this much, and in water its weight is 33.865. so its loss in weight is difference between these two guys. You will get it as how much? Loss of weight in water is 4.385 grams. That is the difference of it, right? So that means this much volume, right? This loss of weight is due to buoyancy, right? So this much loss of weight is happened because this much volume of water has been displaced. So loss of water or volume of water, right? Volume of water displaced is this much, 4.385 centimeter cube, right? Now, so I cannot volume divided by 1, right? Then only you get centimeter cube. If you don't understand, I'm taking it again. So this much gram mass of water has been displaced, right? So the volume is equal to mass by density, and that means 4385 grams of water has been displaced divided by density of water is 1 in gram, right? So that means I can just write it down as 4.385 centimeter cube, right? Clear? Now that means this much of volume of water is displaced, right? This is the how much? 4.1.3. This is the volume, total volume of the gold piece. So this much volume of water displaced, this much is the volume of the entire what? Gold piece. So what will be the hollow space volume? It will be the difference of these two guys, right? So the volume of hollow portion is 4.385 minus 4.113. You will get 0.272 centimeter cube. We have done a question like this, so it is just a repetition, right? Now next question, which is a number, I believe it is 9. Right, a hollow sphere, a small hollow sphere which has a small hole in it, is immersed in a water to a depth of 40 centimeter before any water penetrates into it. If the surface tension of water is given as 0.075 Newton per meter, we'll find the radius of the hole, right? Clear? So there is a sphere, it is having a hole. Before it is water is entering into the hole, it is reaching to a height of 40 centimeter depth, right? This much is clear. So you are asked if the surface tension is given, you are asked what is the radius of the hole, not the sphere. Okay, yeah. So when the hollow sphere with a hole is immersed in water, an air bubble will be formed in the hole, right? So the water will enter the hollow sphere when the pressure exerted by the water column becomes equal to the excess pressure inside the air bubble. If you don't understand, I am repeating. This is the hollow sphere. So this had a cavity, right? Cavity or a hole, right, drilled into it. So once it is dipped in water, this much portion will be actually occupied by with a bubble, right? So the water will enter this hollow sphere, right, when the pressure exerted by this much water column, right, is equal to the excess pressure inside the air bubble, right? This air bubble has to be replaced by water, right? So what is the pressure due to this air or water column? It is H rho G, right? If this is the H, right, that should be equal to, this is a what, bubble inside the water, so it is 2s by r, only one free space, right? From here you can find the radius of the sphere, this r is equal to 2s by h rho g. Then you substitute the values, you will get the answer as 3.8 into 10 to power minus 5 meter. That is the radius of the hole. This one's not the spheres, holes. Clear? Right. Now the next question, 10th one. Right. A body is floating in water with 1/4 of its volume. This is like this. 1/4 of its volume above the surface of water. So that means 3/4 is below to the water. Right. Right. If placed in oil, this is in water. Right. Now we are going to keep the same thing in oil. Right. So if placed in oil, it floats with 1/3 of the volume above the surface. That means 2/3 will be downwards, 2v/3 down, right? Find the density of the oil in gram centimeter or gram per centimeter cube, right? This is a question, right? See, if let's say capital V is the volume of the entire body, so here you have understood 3/4 is inside, right? And that in the inside, in the case of oil, it is 2/3V. I have shown in the figure itself, right? See, that means if rho is the density of oil in, right, or density of oil in gram per centimeter cube, then they should have same pressure, that is the weight displaced. See, let me make it clear. This is floating because the buoyancy here is balancing the weight, this much weight, or this much weight or weight of the block, that is buoyancy, or I can say weight of water displaced is equal to weight of the, what was it, this body. Then only this floats, right? Similarly, this floats when weight of oil displaced is equal to weight of body, right? This you have learned earlier, right? So that means weight of water displaced should be equal to weight of oil displaced, right? So what, right, because their RHS is same, right? So what is weight of water displaced? It is V rho G, right? That is how much is V inside, that is 3/4 V. Density of water is 1 and G is equal to, what is the weight of oil displaced? It is 2/3 V. Density of oil we don't know, into G. G cancel, V cancel. So you can find density as of oil as 9/8. Simple. Again, it's a conceptual question. Now I have shown the questions, guys. So I believe you can see the 25th question. Ice is floating in water such that 90% of its volume is under the water. In a new planet where the acceleration due to gravity is 10 times that on Earth, ice floats in water. What fraction of volume will be submerged in water? Right. So it is said that in Earth, right, ice is floating such that 90% of its volume is under the water and 10% is above. If it is moved to another planet where the acceleration due to gravity is 10 times that is 10 g, then what will be the volume which is inside the water? See, you need not do any calculation. How much volume is inside and outside doesn't depend upon acceleration due to gravity. right? It depends upon how much volume of water is displaced, right? So it is irrespective of acceleration due to gravity. So in the earlier scenario, same water, right, you're having ice. So if it is having ice is 90 percentage below, means in another planet in the same water, again the ice will be 90 percentage below itself. Clear? So I hope you got the expression as 9 by 10, 90 percentage. Right? Clear? Right. We'll remove this one. Okay. So moving on to the next problem. The next one is this one. Two immiscible liquids. Immiscible means they are not going to mix up. Of density is 1.2 grams per centimeter cube. That's gm per cc. Right? And 1.6 gmcc are kept in a cylindrical vessel. The height of the liquid columns are equal, right? A solid cylinder of density is given 1.5 gram per centimeter, is floating with 1 by 4th of its length in the denser liquid. That is, denser means which is having higher density. It is a 1 by 0.6 section, it is having more. 1 by 4th is inside there, and that means 3 by 4th part will be in the rarer medium. Density of the material of the cylinder is being asked. It's a very good question, concept question. So I'm going to take a tank like this, right? And let me draw this liquid as a dot, and okay, equal length, na? So this is another section. Okay, so let's take this liquid as dash, right? This one's density is 1 point, how much? 1.6 1.2, right? So let me write this density as 1.2, right? Let's take this as rho 1, and this one's density rho 2 is equal to 1.6, right? And there is a, okay, we make the structure proper. Let's take another color. No, green cannot be seen. Let's take yellow. Sorry. Right? So this is the cube inside it, right? So that this much length is L by 4 and this much length is 3L by 4. As per the question, this much has been given, right? Clear? And you are asked what is the density of what? The cube or the cylinder. I said cylinder, right? So how will we solve this question? See, that means the weight of cylinder is balanced by the upthrust which is provided by both these liquids, right? That is, I can write here weight of cylinder, right, is equal to upthrust by liquids, both the liquids, right? So what is the weight of the cylinder, right? That is volume of the cylinder, that is length of the cylinder into, volume of the cylinder, density of the cylinder into G, right? That is equal to, what is the upthrust which is given by the liquids? Let us talk about this liquid. It is having L by 4 length, right? The volume of the upthrust means I can say volume displaced by, or how much volume is displaced by this liquid, right? Or the weight of the liquid displaced, right? So how much is the weight displaced by the liquid? How much liquid has been displaced? That is the volume of the liquid displaced, right, into density of that liquid, that is 1.6, right, into G. Now how much volume of liquid is displaced? How much cube is inside it, or how much cylinder is inside it? L by 4, right, into area, then only volume, right? And there is an into here, I missed out. Okay, I will put a dot here, so I hope you understand there is into, right? Plus similarly the above liquid also has 3 by 4 L, right, into A, into 1.2 is the density of that liquid, into G. Now you can find the draw, right? Clear? Okay, if you have problem with this volume, can be also written as length, total length into total area, right? That is a cross-sectional area. Now from here A cancels out, you can find the density of the block. You will find it as 1.3 gram per centimeter cube. Clear? Right, calculation is from your part, has to be done. Right, simple. Right, now where is the question now? Right, so let us move on to this one, 27th question. Okay, this is actually the this is a numerical question with numbers. This one is without numbers. Right, so I can believe, or by believe you guys can do this question. See here, in place of 1.2 etc., you are given parameters rho, m rho etc. See, so this is actually the same question in different terms. Now let us move on to the 28th question. A piece of brass, right, alloy and coppers mix, weighs this much in air. When weighed in water, it has an apparent loss of weight. That means its weight has been reduced. So it will be okay. Loss and weight is already given, then it's very good. If the relative densities of copper and zinc respectively, you are given separate. Copper and zinc's density is 8.9 and 7.1. You're asked what is the copper in the alloy, amount of copper inside the alloy. This is a very good question. Again, it's a concept based question, guys. Let me first remove this much portion of it. Okay, so let's move on. Let us say if this is the alloy, inside this alloy I'm going to consider m is the mass of copper inside it, right? Then the volume of copper will be mass by density, that is mass divided by 8.9. This is the volume of copper inside this material, right? Similarly, if this is the volume of copper, then volume of zinc will be, out of this m mass is copper, right? So total mass is 12.9. Out of this, if I reduce the mass of copper, I got the mass of zinc. That divided by density, that is 7.1, gives you the volume of zinc, right? Now what is the total volume of this material or the alloy? This volume of copper plus volume of zinc, that is m by 8.9 plus 12.9 minus m divided by 7.1, right? This is the total volume of alloy, right? Now what has been given? You are told that there is apparent loss of weight of brass, right? If this is the total volume of the alloy, which is now completely immersed inside a liquid, that is water, that means it is this much volume, it is dipped, means I can say that the loss of weight is balanced by this one, right? That's how much weight of liquid is displaced is balanced by the volume of the entire alloy, right? So how much is the liquid displaced? That is apparent loss of weight, that is 1.6, right? So this much volume of alloy is equal to this much mass displaced water. This much mass displaced water, and what will be the volume here? This is the mass, right? So volume is equal to mass by mass into density, sorry, and the density is 1. So I can just write the volume of water displaced is 1.6, right? So that will be equal to the volume of alloy, right? So I can equate these two guys and can find m's value as 7.61 gram, or I can write it as 7.61 into 10 to the power minus 3 kilogram. Simple, clear? Let us move on to the next question, guys. Okay, I lost the photograph. Let me take the question. I think I lost the question. We'll do this another one, huh? Yes. This is the last one's homework. I'm so sorry. Taking a lot of time. This one? No. Where did I lose it? This one? Obviously not this one, but let's continue with this one. Sorry. Okay. Okay. Okay, 32 question. A gas capillary tube is immersed in water shows a capillary rise of 4 centimeter. The angle of contact is given as 0. That means it is water. Okay, sorry. 0. If the tube is now immersed in another liquid so that the capillary rise is only 2 centimeter, then the new angle of contact between the glass and the liquid is. So you are told there is a glass capillary tube in water. Its rise is height h is given as 4 centimeter. Angle of contact is 0. If now the tube is inserted in another liquid, the capillary rise is h is given as 2 centimeter. Now what is the angle of contact? It's a simple question, direct question. So let us write. I hope you remember the equation. H is equal to 2s cos theta by r rho g. Right, so I have also told that h by cos theta is always constant. Right, better take this section. Right, so h by cos theta is constant means h by cos theta is equal to h dash by cos theta dash. Now you are given h value as 4, cos theta is cos 0 is 1. Now h dash, that is new level, is 2. Cos theta dash I don't know. Find the value of cos theta dash. Right, you will get theta 1 cos theta dash is equal to 1 by 2. That means theta dash is 60 degrees. Simple question. Right, so you have to learn the capillary rise section. Okay, similarly let's move on to the So 33, two liquids of densities rho 1 and rho 2 having same value surface tensions S rise to the same height into identical capillary tubes. The angle of contact theta 1 and theta will be. What is the relationship? See, H is equal to 2s cos theta by r rho g. Right, now from here I can say you are nothing told about what h etc, height etc are same. So I can write from here that cos theta by rho, right, it's rho now, rho is constant, right, or I can say cos theta 1 rho 1 is equal to cos theta 2 divided by rho 2, right, and we are told that the densities are different, right, that is the density rho 1 is greater than density of the second medium. Then if like this, if rho 1 is greater than rho 2, then obviously cos theta 1 is greater than cos theta 2, right, that is theta 1 if will be less than theta 2 when cos angles are like this, then that means theta 1 is less than theta 2. So there is a capillary rise, that means capillary is rising means the angle should be acute, that is I can say the angle is between 0 and pi by 2. Acute, I hope you understood what this. So that means if I talk about theta and theta 2, I can straight away write like this, right, but theta 1 should be greater than 0. Similarly, theta 2's value should be less than pi by 2. The range should be like this. Clear? Right, it is simple. It is a concept question. Clear? Okay. Where is the next question? Where did I stop? Okay. The excess pressure of inside bubble, so bubble is balanced by a liquid column is given. When the surface tension of the soap bubble is 0.5 centimeter, density of the liquid G is given. You are asked what is the surface tension, right? You are asked what is surface tension. This is a type of question we have done it, but I am doing it again. Soap bubble, right? 4s by r balanced by column h rho g. Find S is equal to h rho g r divided by 4, right? So h is given as 0.05. Density, no, r is given as 0.05. You just substitute the values. You're supposed to get the answer is 2.2 into 10 to the power minus 2 Newton per meter. Right, this is all a simple question. That's why I'm not going to take that much of time. Okay. Okay, small lead ball of radius r falls from rest in a viscous fluid, right? Liquid. During this motion, heat is produced due to this viscous force. The rate of production of heat when the ball attains its terminal velocity is proportional to. Now, how would you do that question? See, you have to know what is power and force and velocity relationship. Power is equal to force into velocity. Right. Now, this power or P gives you actually the rate of heat production. So, I can write power. The viscous force is the force here, right? That is what is given the friction. So, 6 pi eta R, V into V comes, so it is V squared, right? So, I can write P is equal to 6 pi eta R, and this is actually terminal velocity, right? So terminal velocity is expression, I would recommend you write it, gr squared sigma minus rho divided by eta whole square, right? Now from this expression, here there is an r squared and there is an r squared here, right? So r raised to 4 into r is 5. So I can say the heat production is directly proportional to 5th power of radius. Right, clear. Now let us move on to the next question. So water flows through a tube of diameter 2 cm with speed 0.1 meter per second. The coefficient of viscosity is given. You're asked what is the Reynolds number. So you have to remember Reynolds numbers expression. Right. So what is Reynolds numbers expression? Re is equal to V rho d divided by eta. That is equal to 0.1 into 10 to power 3, that is the density, day into, that is 10 to power minus 2, the viscosity is 10 to power minus 3, you will get 2000 as answer. Clear? I'm so sorry. Okay, let's move on. Now 37. Right, an incompressible fluid flows steadily through a horizontal cylindrical pipe of radius 3r at point A and radius r at point B, further beyond along the flow direction. If the velocity at point A is 50 centimeters second, then what is the velocity at point B? Again, it is simple. It is based on equation of continuity. A1 V1 is equal to A2 V2. It is AV is equal to constant. Right. So A is pi r square. Right, so here will be pi, here also there will be pi, so I will recommend we remove the pi section. So let us take RA squared into VA is equal to RB squared into VB, right? That is VB is equal to VA into RA squared divided by RB squared, right? So what is velocity at the end? A, 50, radius is thrice, right? So you will get the answer as 9 into 5, that is 450 centimeter per second, or it is 4.5 meter per second. Simple question, simple answer. All right, let us move on to the next question. Okay, what is the question? A cylindrical tank 1 meter radius rests on a platform 3 meter high. Initially, the tank is filled with water to a height of 2 meters from the bottom of the tank. If an orifice is made at the bottom of the tank, then the speed with which the water strikes the ground. Right. I'm reading the question. A cylindrical tank is 1 meter radius. A cylindrical tank of 1 meter radius rests on a platform 3 meter high. This is a platform. It is 3 meter high, and on side that there is a cylindrical tank. It is 1 meter, this is 3 meter, right? Initially the tank is filled to the height of 2 meter from the bottom of the tank. 1 meter radius, 1 meter radius, this one. Let's say this tank is having height h, okay, right? And the tank is filled till 2 meter only. Then the speed with which the water strikes the ground is. Hope you have understood the question now. I have drawn the figure. Radius is 1 meter. I forgot to. Right. This is the scenario. So a orifice is made at the bottom, right? Even if the figure doesn't look like a bottom, like this, right? So he asks what is the velocity by which it is this is something which you have actually learned in the case of application of Bernoulli's theorem, right? So you have learned when the water comes out like this from an orifice, it is just like a free falling body from a height from the surface. See, if an object is from this surface, what will be the velocity? It will be root of 2gh. Now what is the height? This is 2 plus 3, it is 5, right? So now you can calculate, you will find it as 10 meter per second. So the velocity of water from here is 10 meter per second. So I hope you remember the velocity of liquid coming from an orifice is equal to the velocity of an object which was kept at a height from the surface. This is the surface, right? That surface point is at a distance 2 plus 3 meter from the ground, right? So its velocity will be this much. So that is the same velocity as that of the liquid which is coming from this orifice. I hope you understood. Simple question, right? I lost the photograph. Okay, better I take another one, right? Should I have another one? Question will be there. This was the photograph I believe we took. Now I got the questions. Okay, see 29th question, right? So a square film of liquid is extended from 2 centimeter to 4 centimeter, and the work done is given. What is the value of surface tension? So let us do this one. Okay, so first area is 2 into 2, that is 4 centimeters square, and the second area increased is 16 centimeters square. So what is the change in area? It is 16 minus 4, that is 24 centimeters square, right? Why did I write 24 is two sides are there, right? So 16 minus 4 is how much? 12. Two free surfaces means it will be 24 centimeters square. I hope you understood. There is a change in area. Now work done is equal to actually surface area or surface energy, that is change in area into surface tension. So I can write work done has been given as how much? 2 into 10 to power minus 4. I'm so sorry for the disturbance, guys. Can't do anything about it. 24 into 10 to power minus 4, that is surface area, and the surface tension is S. You can find S is equal to 1 by 12, or it is 0.08 Newton per meter. Clear? My son is crying like anything. So 30th question, I hope you remember the equation etc. Now going to do it again. You guys can do this one, right? Work done to require to split a liquid drop into 27 identical droplets. Now water rises in a capillary tube to a height of 2 centimeter. In another capillary tube the height is 1/3 of the first. Water rises to the height. I hope you remember this section. If not, it is a capillary rise. So H is equal to 2s cos theta divided by r rho g. Now this is constant, and similarly you are given the same liquid concept, right? Let me consider water rise in the head in another capillary tube radius, right? Water will rise to, so they are having same liquid means which is constant here? S is constant. So I can take S is equal to H r rho g divided by 2 cos theta. So this is constant here, right? So then means H and R, that is only parameter which can either change, the other are constant. So H1 R1 is equal to R2, right? So I can write H2 is equal to H1 R1 divided by R2, right? Now H1 is 2 into 10 to power minus 2, and R1 I don't know. And the second case rises only 1/3 of the first, so I will write it as R1 by 3. You will get the value as 6 into 10 to power minus 2 meter. Clear? Right? So let us move on to the next one. The next question, at what speed will the velocity head of stream of water be equal to 20 centimeter of mercury column? That is velocity head. That is velocity head is equal to 20 centimeter of mercury column. So I'm going to convert this 20 centimeter of mercury column into water column section, right? So it is 20 centimeter into 13.6, that is the density of the water mercury columns, into I'm going to convert it into water column. So that means I will be multiplying it with 1, right? So if you don't know, just understand, if there is an h centimeter of mercury, right, when I convert it into water column, you just have to multiply it with 13.6, right? So there is 20 centimeter of mercury column, means it is 20 into 13.6 centimeter of water. This much clear? Now what do you mean by velocity head? It is v squared by 2g, that is equal to 20 into 13.6 of water. That is what is the question given. Now v squared I don't know, divided by 2 into g, I am going to convert it into centimeter section, so it becomes 1000 centimeter per second square, that is equal to 20 into 13.6, right? Now from here I can write v squared is equal to 20 into 13.6 into 2 into 1000, right? From here you can find v's value is equal to 2 into 13.6 meter per second. Clear? So this 140th question, sorry. So what has been the question? In a horizontal pipeline, okay, this one now, right? In a horizontal pipeline of uniform area, the cross section, the pressure falls by 5 Newton per meter square between 2 points separated by 500 meter. What is the change in kinetic energy per kilogram of oil flowing between these points? That is, the density is given as 800 kilogram per meter cube. So it's a simple question actually, right? So it is like pipe section, right? So definitely you have to think about Bernoulli's theorem. So it is a horizontal pipe, so you can neglect the case of what, the case of our what, sorry, the case of our height section. So Bernoulli's theorems, it is 1 by 2 section, both of the section you can write this as p1 minus p2 divided by rho is equal to half v2 squared minus v1 squared. You can generate this from the Bernoulli's theorem, right? So this is actually your kinetic energy per kilogram, right? So this is your actual value you are supposed to find, that is p1 minus p2 by rho, that is 5 divided by 800, that will be 6.25 into 10 to the power minus 3 joule per kilogram. Okay, doubt how that expression came up, I have derived it here. This is our Bernoulli's theorem. I have just divided rho throughout, so this equation becomes like this. This is the same equation I have written here, right? I have just rearranged, see. So p1 by rho minus p2 by rho, or I can write it as p1 minus p2 by rho. p1 minus p2 by rho is equal to half v2 squared minus v1 squared. That is what I have written above. So this is the expression for change in kinetic energy per kilogram, right? So I just found sometimes you might be thinking why this equation came up. That's why I derived it again. And to do this one, I'm sorry if it is not, clarity is not there, I will tell you. So there is a branching in this pipe. This one's parameters given as 4 centimeter squared, 8 centimeter per second is the velocity of water here, or the liquid. What is given here? Fluid. Okay, here the parameter is 2 centimeter, 2 and 5, that is 2 centimeter squared, 5 centimeter per second. Here this one, straight pipes, this one is 1 and 10, 1 centimeter squared area and 10 centimeter per second, and this one's parameter is given 3 and v. 3 centimeter squared is the area of this pipe, and v is the velocity of water or the liquid coming up. Here asked what is v's value. Simple question, you guys can actually solve it by yourself. So based on our what, equation of continuity, av will be equal to a1 v1 plus a2 v2 plus a3 v3, right? This is coming in, the 3 are leaving, that's why I written like this. So 4 into 8 is equal to 2 into 5 plus 1 into 10 plus 3 into v. Now from here you can find the value of v. We'll find v is equal to 4 centimeter per second. Clear, right?